Okay, so today we are discussing the role of priority queue in path optimization for robots. Optimization in robotics. The challenge that we face is path optimization means finding the most efficient route for a robot to travel from point A to B in an environment. In grid-based systems, robots must navigate around obstacles, minimize travel distance, and make decisions quickly to operate effectively. Modern robotics face several key challenges: dynamic obstacle avoidance, real-time computation constraints, and the need to balance with speed and accuracy. The right data structures makes all the difference. Understanding priority queues. So in this question, we have used priority queue. A priority queue is an abstract data structure where element has an associated priority value. Unlike regular queues that follow first in first out, priority queue serve elements based on their priority, typically extracting the element with the smallest or largest value first. The key operations is it inserts a new value with priority to its queue, remove and return the element with highest priority, peak, view the highest priority element without removing it. It is priority based and it has efficient access because of OLOG and insert and extract operations. Priority queues are typically implemented using binary heaps, which provides logarithmic time complexity for insertion and extraction operations, crucial for real-time robotics application.
So now I will discuss how priority queues are used in pathfinding algorithms. Modern pathfinding algorithms like Dijkstra's algorithm, A-star algorithm rely heavily on priority queues. To efficiently explore the search space, these algorithms maintain a frontier of nodes to explore, always selecting the most promising candidate next. It starts with initializing the node at a starting position with priority 0. Then go on to explore the neighboring nodes with a calculated cost to the priority queue. Then selecting the best node from the queue and continuing this until the final or the end node is achieved. Dijkstra's algorithm. This algorithm explores nodes based on the cumulative distance from the start. The priority queue ensures we always expand the node with the smallest known distance, guaranteeing the shortest path. A-star search algorithm uses a heuristic to estimate remaining distance to the goal. Here, priority is equivalent to actual cost plus the estimated cost. This guided search finds optimal paths faster than the Dijkstra's algorithm. Transforming robotic navigation. Here, priority queues enable robots to discover efficient routes quickly and reliably. By intelligently ordering which paths to explore first, robots can navigate complex environments with minimal computation time and finding optimal results. It leads to faster path discovery. Exploring nodes in priority order reduces unnecessary computation by up to 70%. Optimal route selection, which guarantees finding the shortest path or the least cost path, and reducing computation by using efficient data structure to enable real-time decision making. If without priority queues, or the using normal queues, it leads to random or sequential node exploration, many unnecessary paths checked, and slow convergence to a solution with higher computational overhead. With priority queues, it leads to intelligent and cost-based exploration focused on most promising paths, rapid optimal solution discovery with minimal costed computation. Smarter paths start with smarter data structure. Priority queues are fundamental to efficient robotic navigation system. By enabling algorithms like Dijkstra's and E-star to intelligently explore search spaces, they make real-time path optimization possible in complex dynamic environments. Priority queues and E-star search algorithm is used in autonomous delivery, where last mile delivery robots navigate sidewalks and street using priority queues to find optimal routes while avoiding pedestrians and obstacles. Warehouse automation, where thousands of robots coordinate movements in fulfillment centers, each using efficient pathfinding to minimize travel time and maximize output. Aerial routes, such as UAVs, which plan flight paths in 3D space for surveying delivery inspection tasks. The choice of data structure isn't just an implementation detail, it's the foundation of an intelligent robotic behavior. Thank you.
Okay, so here I'm explaining the implementation, the setup and structure of a problem statement. So the core components are the type definition and help struct, the nodal cost node repar, just cleaner type names. The minimum cost comparator makes priority queue work as a minimum heap, which is smallest cost first. The grid pathfinder class is a data member. The grid width and height are grid dimensions. The adjacency list stores connections between cells, like which cells connect to which. Obstacle nodes block cells you can't walk through. Dijkstra predecessors and A star predecessors, which tracks the parent nodes to reconstruct the path. Coordinate convergent functions, we convert x to y to single id, row and width plus column. The id to coordinates reverses to get x and y back from the id. Example, in a 10 by 10 grid 9 comma 9, which is the x coordinate and y coordinate, the id will be 99. Grid initialization, we initialize nodes, create empty adjacency list for every cell, set obstacle, which is column and row, mark cells as block, construct grid graph, the key function, which checks four directions, up, down, left, and right for each cell. If neighbor exists in bounds and not blocked, add correction with cost 1. Result where graph where walkable cells connect to neighbors. Helper functions. Reconstruct path which follows parent pointers backward from goal to start, then reverse display solution. Creates visual grid with symbols. S as start, goal, block, path, and explore. The estimate chord is the Manhattan distance heuristic, which is x2 minus x1, the whole modulus, plus y2 minus y1, the whole modulus.
So we'll explore the next following function. The execute Dijkstra's algorithm. This function executes or performs the Dijkstra's algorithm. We first introduce an unordered map, G-score, and a close and another unordered set to store the paths which have been already been explored. The, we initialize the first node G-score with the distance traveled as 0. Then we push the starting node and its value or the distance traveled into the min heap or the priority queue. We then continuously calculate the current distance, current nodes, adjacent neighbors, and their distance and the distance they have traveled, and then based on the shortest distance, we append it to the minimum heap. In this path, if no path has been found, access would return no path found. This code executes A star search algorithm. Here, unlike Dijkstra's algorithm, we not only store the paths, the distance we have traveled yet, but it also scores the F score, which is the current distance plus the heuristic distance that we have calculated. Initially, we fill all of the distances into all of the G score and F score with the maximum value. Then we first calculate the initial heuristic, that is the heuristic distance from the current node to the end node, and push the current node with the F score into the minimum heap. Then, similar to Dijkstra's algorithm, we calculate the neighbors of the current node, and based on the neighbors of the current node, we calculate the minimum distance between them and push them to the minimum heap. But unlike Dijkstra's, here the comparison is made using F score. We push the F score into the minimum heap instead of the G score. And if no path for A star has been found, it returns. The void compare compares the two algorithms. It's a helper function. Now in the main function, we create a 10 by 10 grid The solver dot of set obstacles sets obstacles in the graph. Solver dot construct grid would create the grid graph, and solver dot compare algorithms would return us how both the algorithms have performed in the grid. Now let's see the output of this code. As we can see, in the pathfinding algorithm comparison test for a grid size of 10 by 10, Dijkstra's algorithm, the total path cost was 80. The nodes that Dijkstra's algorithm visited before finding the minimum path or the most optimal path were 93. While in A star search summary, the optimal path cost, the G score, was 18, similar to Dijkstra's, but the number of nodes evaluated were much lesser than Dijkstra's algorithm, indicating A star search is much more faster than Dijkstra's.
Hi, I'm Prathamesh. I'm from Group 16 and I reviewed your path optimization code for robot using A star algorithm and I have some questions about it.
Uh,
Yeah, I'm Bhargav from Group 5. I'm ready for all of the questions and doubts you have on our code.
Okay then, here I go. My first question is what makes your A star search algorithm more efficient than the used Dijkstra's algorithm?
Uh, that's a very good question. So, the Dijkstra's algorithm, what it does, it explores nodes on the basis of how much distance it has traveled till now, which which is efficient. But the problem with the Dijkstra's algorithm is it never considers how far the current node is from the final node. This problem was changed using the A-star search algorithm, which is a modification of Dijkstra's algorithm. A-star search algorithm calculates a heuristic distance from the current node to the end node and adds it to the path the current node has traveled. The current agent has yet traveled, and on basis of that, it passes the agent value or the current node information to the priority queue. A-star search, although it consumes more space, it is much more efficient than Dijkstra's algorithm as it does not explore nodes mindlessly and only focuses on nodes which are closer to the endpoint.
That's pretty cool.
Okay, I want to ask that how did you choose or design a heuristic so A star stays optimal but run faster?
okay, so that's a very good question. First of all, we pick a heuristic that is admissible, so we never overestimate the true cost. So to guarantee optimality, we prefer consistent heuristics to avoid reopening nodes. We use domain knowledge, Manhattan for four connected grids, Euclidean for two continuous 2D free space, with a pre-computed lower bound, like a distance on a course roadmap. Stronger but largely admissible heuristics reduce explored nodes, but if you overestimate, you lose your optimality.
Alright, that was pretty cool. I have another question for you, Bhargav. If this were to apply to a real world robot instead of a grid environment, what changes would be needed according to you?
The immediate changes that would be required for it to work in a real world environment, the most important would be to change the heuristic that we have used. In grid based environment, the Manhattan heuristic is most commonly used, but it wouldn't be applicable in the real world scenario where there are real world coordinates instead of just uh, grid positions. So for real world coordinates, Euclidean heuristic will be the most efficient heuristic should be used. Secondly, I would address the issue of dynamic obstacle where in real world scenario, instead like in grid scenario, the obstacle wouldn't move from its place. But in real world scenario, obstacles may be dynamic. They may change places. So using So tackling these problems would be one of the things. And lastly, the way we showcase the movement of the agent would be changed. Instead of showing the grid positions, the cell indices, we would indicate it using real world coordinates.
That pretty much answers all our questions, Bhargav and Sahil. Thank you for your time.
You're
Thank you
welcome.
so much. We were happy to answer your questions.